everyone here. Thank you for coming. And today we're so glad to have Professor Falson here for our first speaker series webinar. So let me introduce you to our schedule today. Oops. Okay. First, we will give you an introduction to Professor Falson, and then we'll hear his talk, and then we'll have our guided Q&A session. And also, all the participants will have a chance to ask their own questions to Professor Falson. And finally, we'll close it off with a thank you and a post-event survey. So some housekeeping rules to keep in mind will be that please make sure that your video is off during this event, so for live streaming purposes. And make sure, as you might have seen in the chat, we dropped down a YouTube link. Make sure you share with your friends so they can be part of this event as well. And lastly, there will be an opportunity, like I said, for a Q&A session where you will have a chance to ask your questions to Professor Falson. Thank you. And I will pass it on to Abby.
We would like to introduce our speaker today, Professor Joseph Falson from Caltech. Joseph Falson grew up in Australia, where he completed his Bachelor of Science. He then moved to Japan to complete his PhD at the University of Tokyo to learn about crystal growth and materials physics. After graduation, he joined the Max Planck Institute in Stuttgart, Germany as a researcher and studied the physics of electrons at low temperature. He is now a professor of material science at Caltech. And once again, please remember to keep your video and audio off for the duration of the talk. And please save your questions for the end of this webinar, and we'll have a portion when you all can interact. And without further ado, we'd like to hand it off to Professor Falson and have him take it away.
Thank you very much. I'm not able to share while somebody else is sharing. Yeah, okay, fantastic. Let me get started here. So first of all, let me extend my big thanks to the organizers for making this event happen. I think it's a really outstanding series. I really appreciate the the effort that you must have to go to reach out to a broad audience of young people who are just starting to think about beginning their journey in STEM or science and basic research, which I'll be talking about today, or fundamental research is the term that I'm using. So, I'm hoping that this is somewhat useful for you today, this discussion. It's hopefully not too technical, but please forgive me at times. I'm going to be using a little bit of technical jargon. This is just a force of habit, but hopefully I'm able to convey to you at least kind of the motivating principles that we have in the realm of fundamental research, hopefully convey to you how it's important, hopefully convey to you my enthusiasm for fundamental research and how I love my job. I love working with my team. I love the problems that we tackle. And that I think it's really important to both fund and invest and have a long-term vision for the role that fundamental research plays in society. So as Abby said, my name's Joseph Falson. I'm an assistant professor in the Department of Applied Physics and Materials Science at Caltech. This title, assistant professor, means that I'm a relatively new member of the faculty at Caltech. I'm setting up a new lab. We're going to be doing a lot of interesting materials physics there with a very much focus on the fundamental properties of these materials and trying to discover some qualitatively new behavior. So the presentation outline is fairly simple today. I'll be kind of jumping between these bubbles a little bit. Really the question or the topic I'd like to discuss at length is really the difference between fundamental and applied research. So, I can understand that, as coming out of high school, coming into university, even coming into grad school, you may not have a great perception of the roles that fundamental and applied research play, and how to get involved in these and which one is really suited to your personality, because there's no, correct answer. When it comes to the latter facet, at least, you really need to find your way in and kind of find a field of research which is stimulating to you. And then that's going to lead me to my next point about what excites scientists, and this is particularly in the realm of fundamental research. And this is kind of what are overarching, themes which really excite the community and get us, scratching our heads and fighting against each other and trying to come up with ingenious solutions or ingenious explanations for what seem like incredibly complex problems. And then finally, I'll be touching on kind of the idea of towards quantum materials. So today the talk will be very much revolving around the idea of materials research, because this is my specialty in the Department of Applied Physics and Materials Science. We make crystals, we investigate their physics, we investigate their chemistry, and kind of the buzzwords that you currently hear in this field is kind of quantum materials and emergent properties and these type of words. So I'm hoping that I can give you a little bit of an outlook of kind of where the field is and where we're hoping to go in the future. So, not so long ago, I was, in a position of finishing high school, entering the undergrad university. I have a couple of slides at the end of this talk where I'll be able to talk about, the specifics of my journal, actually, my journey actually getting to this point. But I remember very clearly in high school being given a choice of, you have 4 classes, they're all kind of STEM classes, and you have to choose maybe 2 of them or something like that. And that was kind of my very, one-dimensional view of what STEM is, what research is. And, it takes a lot of time to kind of grow beyond that and understand that actually research is a very interdisciplinary and very kind of complex web of problems, and they're all interlinked. So I remember being posed with the question, do you want to do mathematics, physics, chemistry, or biology? This was it. This is the library of natural sciences in high school. But, things begin to change as you enter undergrad. Suddenly you're enrolling in your classes, right? And you're given all of these choices, depending, if you're a science undergrad, you're probably going to have to be doing some mathematics, some physics, some chemistry, and probably some biology as well. But as you go up into the upper level classes, you really realize that each of these disciplines is really, it has extreme subdivisions and extreme degrees of specialization, even within some broad umbrella of saying, a major in chemistry. So my undergraduate degree was in chemistry. I took classes in organic chemistry, a little bit of organic chemistry, analytical chemistry, but kind of my career naturally evolved to kind of take me more in the left-hand direction of this library. So what I'll be talking about today, if you're talking about in kind of upper level undergrad terms, is very much in the realm of statistical mechanics, thermodynamics, quantum mechanics, solid state physics, physical chemistry, and inorganic chemistry. It's somewhere at the borderline of physics and chemistry. And that's why I think it's really exciting, because we're, modern science, as I said, is very interdisciplinary, and to have kind of a breadth of knowledge and a breadth of interests, it kind of I believe it's definitely a positive for one's career. So this won't be a talk on biology, it won't be a talk on mathematics. It's going to be somewhere in the realm of solid state physics / solid state chemistry. So, when I'm talking about solid state physics, this is generally speaking a class that you'll take maybe in 3rd year of undergrad, maybe 4th year of undergrad. It's kind of a fairly upper level class. But if you really want to boil this down into kind of one sentence about what is solid state physics, it can really be boiled down into the concept of understanding the electronic or the optical properties of matter, and more specifically crystalline matter, so crystals. And, hopefully I'm just going to give you a little bit of a crash course in kind of introductory solid state physics. So this will lead you into an understanding of what the problems are and kind of the history of how we have society as it is, because this is really vested in these developments that have come out of solid state physics. So most of the matter around us, and especially the electronic and optical matter, is made up of crystalline solids. And when I say a crystal, this just means it's a repeating pattern of a large number of atoms which have condensed into a solid phase. And this is why we call it solid state physics, because we're not dealing with liquids or gases or anything like that. We're dealing with crystals that are in a solid phase, and you can crack them and you can grow them as solid pieces that you can pick up. Now, from a single atom's point of view, these crystals are ginormous, infinitely large. We're talking about 10 to the power of 23 atoms per cubic centimeter or so. So this is an incredibly large amount of matter that we're dealing And generally, you know, when you start thinking about these crystalline materials, you ask yourself, you know, what are the electronic properties? What are the optical properties? And to kind of divide this again into two realms, I'm going to talk about insulators and metals. And in daily life, we're very, you know, well acquainted with insulators and metals. On the left, this is just glass. If you go up to your glass panes and put a, you know, a voltmeter or something across it, it's not going to measure any current going through this glass pane. And that's because it's an insulator. There's no free electrons floating around. So you can apply, I'm hoping that you can see my cursor. You can apply a battery across some junction made of an insulator and no current is going to flow through. Now, in the case of metals, this is the other end of the spectrum. We have lots of little red electrons in this crystalline material. We can apply a battery and a large amount of current is going to flow through this material. So this defines what a metal is. And copper is a famous example. You know, most of the wires in our electronics are made of copper, and that's because it's very low resistance. The electrons can flow very freely through copper, and they don't generate a lot of heat in the process of scattering. But a big question that science had, you know, approximately 100 years ago now is, can a material be both a metal and an insulator? And it turns out it can. This is what we define as what's called a semiconductor. Perhaps you've heard of the word semiconductor, but basically what this means is, generally speaking, you start with an insulating material and it's off. So this is kind of similar to a piece of glass. The most famous semiconductor is either silicon or germanium. And what we can do is we can attach two electrical contacts at two ends, and then we can add a third electrical contact, which is a gate. Now, this gate is actually kind of spatially separated. It's not actually touching this semiconducting material. But now imagine that I apply a voltage to this gate. What it's going to do is I'm going to put a positive voltage on this gate. It's going to have an electric field which goes down to this semiconducting material, and it's going to attract these electrons, just because, you know, these negatively charged electrons are attracted to a positively charged gate. So now this accumulates carriers in this semiconducting material, and suddenly it's a metal. So now we can switch between on and off just by applying an extra voltage here on what's called a gate. And now this is a switch. This is basically, you know, this is our semiconducting switch, which we use in all of our integrated circuits. And this is what we call a transistor, the ability to turn a semiconducting material on and off. This is a transistor device. Now, I'm hoping that you've heard of transistors and the role that they play in modern society. So you're looking at a computer screen right now, and inside your computer is something on the order of a billion transistors. And this is, you know, a great example of applied research, industrial scale research, where we have investigated every single aspect of these transistors, this semiconducting material, which in this case is silicon, and basically perfected this. So what I'm plotting here is, this is the number of transistors in an integrated circuit versus time. So this is back in 1970 up to approximately today. This is a person called Gordon Moore. He's the founder of Intel Corporation, and I'm sure you've all heard of Intel. He's from Caltech originally, and he has been instrumental in the field of semiconducting materials by leading Intel. And basically, he coined the term Moore's Law. Now, you've probably heard of this. This is basically saying that every 18 months, the number of transistors in an integrated circuit is going to double. And this is what this slope is. This is showing that, you know, we haven't had ups and downs very much. There's no, you know, waves here on this line. It's pretty much a straight line going up in time, just showing that we're adding more and more transistors by making them smaller effectively and just mastering the processes. So here's one example on the right-hand side. This is what's called a transmission electron microscope image. So we're looking, you know, at very small scales here. This is kind of 30 nanometers or something like this. And this is called a FinFET, where this is like a fin and a field effect transistor. So, you know, Intel is now in the regime of mastering all of these very complex structures, just to pack as many transistors onto these circuits as you possibly can. And really what underpins this, you know, I'm a materials person. I love crystals. I love growing things to ultimate purity. Yeah, these type of amazing procedures, these amazing experimental procedures where this is a human being for scale. And what this person is holding here by this little thread up here is probably a couple of 100 kilograms of solid silicon. So this is a crystal which is basically perfect. there's no defects in there. There's no cracks. There's no rotations. There's no other atoms, these type of junk in there. I mean, there is a little bit of other atoms, but strictly speaking, this is basically pure. So these ultra pure silicon crystals are really what underpin all of this advancement. And then you take it to the next step by, mastering how you actually want to process this silicon. But, let's rewind a second. This is kind of 50 years of advancements, right? And this certainly, took, an unfathomable amount of man hours. So, this is where I want to start to highlight, the value of fundamental research by showing you that, what we're seeing here, this is pretty advanced stuff. And in reality, what you do in a lab is much more rudimentary. It's much more exploratory. It's much more challenging, because you're having to use your imagination to actually demonstrate a new principle. And this is what fundamental research is, demonstrating qualitatively new ideas rather than quantitative improvements. So believe it or not, this is the first transistor, or at least a reproduction of the first transistor. This is from 1947 in Bell Labs. This is a very famous research facility, which was based out of New York and New Jersey. This is prior to becoming AT&T. This is what is shown, basically. This is your semiconducting material here. This is your gate, and this is your source and your drain on the side. And by pressing this in and applying a gate bias, you could generate charge in the germanium crystal and induce a metallic sheet. So this was Genesis. This is the first transistor. And this was pioneered by these three very gifted individuals, Shockley, Bardeen, and Breton. They all got the Nobel Prize for this. And you'll notice there's actually 2 Nobel Prizes for Bardeen. He was an exceptionally talented scientist who came up with a theory for superconductivity. We'll touch on this very, very shortly later on. And got the Nobel Prize 20 years later for a completely different topic. So he got this twice. And I'd like to point you in the direction of this fantastic book, which kind of goes through the history of these amazing ideas, these fundamental ideas that came out specifically of Bell Labs, kind of from the late 1800s to the early 1900s, where it really, most of the technology underpinning modern society was developed. So, the question is, how do we do this? How do we go from, how do we make that ultra pure silicon? How do we make ultra pure materials in general? Because the silicon is basically from sand, right? So you go to the beach, you're walking along the beach, and what you're seeing on the ground is silicon oxide. Turns out you can purify that and make it into perfect crystals. And what my career has brought to me is something kind of similar. This is actually a powder of zinc oxide. So zinc oxide is in your sunscreen, right? I grew up in Australia on the beach, and every weekend, I'd be lathered in this white material. And it turns out that's zinc oxide. And zinc oxide is in sunscreen because it absorbs UV light. And this is very important for understanding the optoelectronic properties of this material. But how do you go from this junk powder into these beautiful transparent crystals that you can see here? This is kind of where the chemistry begins to come in, right? So even though, we're looking at this with the naked eye and we think, oh, this is just some random powder or something like this, this is actually very pure when you get down to the nanoscale. These are all individual little crystals. So this is what we call a unit cell. The unit cell is just the smallest unit of a crystal that you can get to for any particular material. So what I'm showing you, this is what zinc oxide looks like when you really zoom into the atomic scale. We have oxygen. This is oxidized to 2-. Zinc is in a 2+ oxidation state. It forms this inversion asymmetric material, which gives it beautiful electrical characteristics. And it has these local tetrahedron, which also we can use for various for making various electronic devices. So, if you can identify what the crystal is actually made from, then you can start to think about, oh, maybe there's an experimental apparatus that I can come up with that will allow me to make this in the lab. So I'll get to that apparatus in just a moment, but to really, condense down over a decade worth of effort. This is not all my work, but a fair amount of this is my work. I want to show you how you can take sunscreen, a disordered material in powder form, to single crystal, and then really make this unbelievably clean when you look at the electrical characteristics. So this is a type of plot that we often use in physics. It'll, parameterize, for example, the number of electrons, and we can control this experimentally, the amount of electrons that are in this material. versus the electron mobility. And the electron mobility is basically how clean the material is. It's how fast these electrons can propagate through the material without running into some crack or, disordered atom or something like that and scatter, right? Because if it scatters, if it runs into a wall in the material, it's going to lose its energy and the material is going to heat up. This is what heat is in these electronic wires, dissipation, and this is scattering, right? So we've been able to improve the quality of this material from a number of a few thousand electron mobility up to over 1 million. So this is 3 orders of magnitude improvement. And this all comes about through just dedicated crystal growth, looking at the details, working out the chemistry, and then having a nice feedback mechanism where we study the physics of these carriers and bring it all back in. So exactly, how do we do this? Well, there's many ways to do this. If you want to have a more extensive discussion about crystal growth techniques, it'll be my great pleasure to do so. You can ping me at any time, but I'm just going to demonstrate to you one technique which I'm particularly invested in. This is a technique which we call molecular beam epitaxy. And you can think about this as basically a very, very fancy, very expensive, very slow way to do spray painting of materials. So what we do is we build these big vacuum chambers. These are on the order of maybe 0.5 meter, maybe 2 feet or so in diameter. And we attach big pumps to them. These pumps evacuate the chamber and take the background pressure down to nearly as good as space, not quite as good as space, but quite good. And then we put inside of this something called a substrate, and we can rotate this and heat this up and do whatever we want. But this substrate is just basically a piece of it's a crystal which is going to act as our platform for growth. It's going to be a template, basically, for what we actually want to grow on the surface and do the chemistry on the surface. And this is where the spray painting comes in. So in addition to our substrate, which is sitting in ultra-high vacuum, we have what's called diffusion cells. And these diffusion cells are small crucibles which we heat up to some temperature. And we put some material inside this, and we just slowly evaporate this. So this evaporation process, everyone is familiar with this. Water evaporating, you spray it on hot concrete, it's gone in a few seconds. This is basically what we do in these diffusion cells. We put whatever material we want inside. We can have maybe 10 or 20 diffusion cells in one chamber, and then we evaporate that material onto the substrate, right? And you can think about, if I do this evaporation really slow, if you boil this down, these are single atoms that are going onto the surface. And now this opens up the whole world of chemistry, right? And we can put most of the periodic table inside these chambers and do whatever type of surface chemistry we want. This is kind of a rough explanation of what we can perform in my lab at Caltech. We can cover most of the periodic table, not all of it. But it really gives you the freedom to explore a lot of to speak in scientific terms, non-equilibrium phases. So, you can put chemicals together or atoms together that usually don't exist that way in nature. So you can make a lot of artificial crystals. And this opens up completely, limitless realms of exploring, functionalities of these materials. And this is where we enter the materials physics idea, the idea of engineering these materials, not just taking what nature gives us, but saying, oh, well, we learn from nature, but let's go beyond nature. Let's kind of put these materials on top of each other, or make these materials really thin or really small or something like this. So these are the experimental tools that we often put to use. So I just like to add the note, because I like this very much. I think that, scientists are crazy all around the world, and, good on them. Dream big. I think it's fantastic. But, people take this really seriously. This is a demonstration of very similar evaporation tools, molecular beam epitaxy, being performed in space. So they basically emulated this type of vacuum apparatus. But of course, if we're doing it in space, we don't even need the shield around it anymore, right? So they put this up on the space shuttle, and they can hold it out and shield it from the solar winds and perform these type of deposition materials in the ultra high vacuum of space. So, this is all just pushing in the same direction. Let's make it as clean as possible. Let's do it with the most flexibility as possible. And let's go as, to the pure limit, and really try to understand what type of, underlying physics is there. So, a lot of the time, when you discover an interesting material, and there's a lot of interesting materials out there, it just depends what you want to actually do with it. you're often tasked with the problem now of, how do I make it clean? And this is what I've been saying, silicon has been made pure by these beautiful crystal growers. We try to do it in ultra high vacuum. Some people go to space and do it. So you can really boil down a lot of the problem. How do we take a cobblestone road in a European village and pave it into a beautiful highway? And I mean this in the sense that, we're dealing with electrons no matter what. It's very difficult. I don't know a way to change these electrons fundamentally, right? This is a fundamental particle of nature. And you can think about kind of an analogy of if you take a Ferrari, somebody gives you a Ferrari and you're driving down a street in Europe or something. If you take it down a cobblestone street, you have no idea of the performance of this vehicle, right? There's no way that you can gun it down the street or go around any corners. But you take it to a highway or a racetrack or something, and finally you get to see the amazing physics that is really underneath the bonnet, underneath the hood in this Ferrari. And this is very much what we need to do in this materials engineering, this materials physics realm. We try to build these materials which we think are interesting, and then we purify them, and we try to see the delicate physics which is hidden below the surface. And this leads me to the idea of pinball with electrons. Let me just show you a little bit of some of the experiments that we performed. I'm assuming that everyone here knows pinball. When I was growing up, this was kind of a dying piece of apparatus. Unfortunately, pinball parlors were kind of going out of business. But basically, you take a ball and you put it on some trajectory, and it bounces off all these things, and you try to bounce it around, and you basically study the trajectory of some steel ball amongst obstacles, right? And you think, well, that's probably really difficult to do in a real experiment, like in a conducting material. I can't even see these electrons, right? They're tiny. I don't have a microscope where I can see electrons moving around. But it turns out if we have suitably pure materials and we go to low enough temperature, we can basically play pinball with these electrons. So here's a little experiment that we do. What I've shown just in a cartoon sense at the top of this page here is this is a piece of a crystal, just painted white. Don't take it too literally. It's not a specific material. And in one section, we have a nice clean piece of material. In another section, we have what we call a patterned piece of material. And in this other patterned piece, we dig a whole bunch of holes in the surface. And we have tools which we can do this. This is a very trivial thing. We can go and do this in about 10 minutes, no problem at all. And then we put our electrical contacts on the edges, right? And then we can flow a current through, and we can measure the current, or we can measure the resistance, or we can measure the voltage. These are all lab things that we do every day. If I look at the black resistance here, this is an unpatterned area. What is happening here is this is magnetic field running across the page. Magnetic field I'll explain in a moment what happens here, but basically what is happening at higher magnetic field, we call these quantum oscillations. They're not relevant for the discussion here. This is just a quantum mechanical effect which happens in a magnetic field. But if you look at lower magnetic field and then start to compare the black and the red, you start to see things are pretty different, right? But now you start to think, oh, well, the red section now has all these holes in it. So what's actually going on here? You might remember from high school physics or first year physics that we have something called a Lorentz force. And this is where an electron is deflected by a magnetic field. You might remember the right-hand rule, right? And this is to understand the deflection direction when a current is interacting with a magnetic field. And basically what we're doing here is that type of experiment. So when I note this as the number 4 or 2 or 1, what's actually happening is we're observing these electrons going around these holes, whether or not there's 4 holes in some orbit, 2 holes, 1 hole. And now this is really opening up a way for us to directly understand the motion of these electrons without ever even looking at them. We can just measure the resistance across a large sample and still be able to understand very microscopic aspects of this electron motion. But this is only possible if you have a really clean and really beautiful material system. Okay, so now I've spoken a lot about silicon. I've spoken a little bit about my research of taking sunscreen, turning it into a super pure material. And now I'd like to introduce, the idea which is, it's not a particularly new idea, but it's a very pervasive idea. And this goes back to when we were talking about Moore's law. So I'm going to confuse myself by saying Moore so many times. Moore's law, I'm sorry. there's a new paradigm, or there is a budding paradigm in condensed matter physics that we're not going to be able to continue Moore's law forever. What we're going to have to do is approach new technology in the sense of more than Moore, right? So silicon is going to be great for classical circuitry for a long time ahead. We've got a lot of advancements to come. We can keep purifying, we can keep enhancing, and we're going to keep going down that route. But silicon is not perfect for all applications. There's a lot of things we need different materials for. And this is really what contributes momentum to the field of materials research. So there's endless examples of new materials coming in really high purity and contributing to technology in a more than Moore sense. But I'd like to show you one which is particularly meaningful. Maybe you don't know about it, but it's in everyone's home. It's completely pervasive in society now. What I'm plotting on the left-hand side is this is the lattice constant. This is just basically the size of the crystal, and this is not particularly important for this discussion. What is important is on the vertical axis, and this is what we call a band gap. The band gap is in a sense basically how strong of a semiconducting material is a material. How strong of a semiconductor is it? So if this band gap is small, it means you can turn the material on and off pretty easily. And this is why silicon, germanium, the widely studied materials are kind of down here. They're pretty easy to turn on and off. Now, there's a whole bunch of different materials: gallium nitride, aluminum nitride, magnesium oxide, zinc sulfide, zinc selenide, and various materials which are more difficult to act as semiconductors just because the gap is bigger. But what's convenient about these large band gaps is that it pushes the optical properties into a different color spectrum. So you might remember that the color of light is correlated with the wavelength, and the wavelength is inversely correlated with the energy, right? If you have a very short wavelength, this is blue and it's higher energy, whereas if it's very long, it goes red and it's low energy, right? And this is why silicon is kind of in the red area down here. It's fairly low energy band gap, whereas blue is all the way up here, and this is where gallium nitride exists, and a few other materials as well. What I'm trying to say in a very long and convoluted way is that silicon is great for circuitry, but it's not sufficient for optical materials. There's other reasons why, but one of the reasons is the small band gap. If we want to make blue LEDs, right, we need to go to different materials, and gallium nitride, as it turns out, was the winner. And this is why these 3 Japanese fellows got the Nobel Prize for discovering a scalable crystal growth, again, materials physics, crystal growth technique, which enabled the mass production or opened the doorway to mass production of gallium nitride PN junctions, also known as light-emitting diodes. This is one here. This is just a blue light-emitting diode. And what you can do, because blue is the highest energy visible photon, visible light that we have, what you can do is you can coat this with some polymer. It's a phosphor material, and this luminesces in different colors. So you excite this material with blue, and then it luminesces in different colors, and it gives white light. So when you look at an LED light, what that is a gallium nitride LED hidden below there. So this is an example. Silicon can't do it. We look for new materials, we look for new growth methods, and it completely revolutionizes society. This is, it's very difficult to understate how important LEDs are, or overstate, LEDs are, because they're essentially, from a solid state physics point of view, a perfect device. They are incredibly efficient, and we will have them for centuries to come. So that was kind of the fundamental. This is probably a lab-based device. They're very happy with this. They get the Nobel Prize, and then here come the engineers, and of course, perfection, right? The value, the cost has gone down by orders of magnitude through the years, and the efficiency, the lumens, this is how bright it is, has gone up by many, many orders of magnitude through the years. Again, the same as silicon. So this is fundamental research going hand in hand with applied research, fundamental research spawning these ideas and leading to decades of advancements for applied researchers to come in and result in quantitative gains, I should say. And new bridges to future technology are really being actively explored by these mega corporations now. This is slides that I've taken from an Intel presentation. This is some years old now, and I just want to say that these companies are very invested in silicon at an industrial scale, that is for sure. But, you know, they look beyond. They're looking at new materials. Here's our good friend gallium nitride, 2D materials, molybdenum disulfide, for example, different shaped materials because the properties changes, nanowires, different fundamental physical properties, for example, spin transport as opposed to charge transport. So these fundamental ideas certainly do percolate through you know, these industrial companies, and hopefully, you know, given sufficient time to mature, they do lead to enhanced advancements. So, okay, I've spoken a lot about some very obvious examples of fundamental research, spurring applied research, changing everyone's lives. Now you might be asking, you know, okay, but what excites fundamental scientists these days? Because transistors, you know, this is a fairly, you know, now it's a well understood piece of equipment, right? We can't keep just studying the fundamentals of transistors forever. We need to ask what excites scientists. And, you know, this is a very subjective point, of course. I'm going to share with you a perspective which I found very inspirational from a book that I read from one of the great scientists that somebody that I respect, and one of the great scientists of our time, in my opinion. And what I'm showing you here is an impressionist representation of the particles of knowledge that we have that form our basis for science. So when you're in high school, undergrad, grad school, you're learning these pieces of information, right? You learn some mathematical concept, some equation for a chemical reaction, something like this. And this is just all these parts that you need to bring together. And you can kind of understand it in pieces. Even when you do quantum mechanics, you can kind of solve simple problems exactly numerically. It feels very good at the time. But, you know, taking that to the next level and finding exciting regimes in research is quite a difficult and abstract process. So what we really look for in the realm of fundamental research is the concept of what's called emergence. And emergence is the idea, and this analogy that I'm talking about was taken from this fantastic book here. To represent this as a piece of art, emergence is the idea that when you look at a Monet picture and you zoom right in, all you can see is this individual random particles. They don't make sense, right? You can understand them. Oh, that's a red splodge. That's kind of green here, and this is long and whatnot. But if you really want to understand, you know, the beauty of the situation, you need to zoom out and look at the system as a whole. And the idea is that all of these dots of color, they come together and they contribute more than their individual components. This is the idea of emergence, in that the system is more than the sum of its parts. The beauty is in its construction, in its assembly, in its organization. And this is really evident. This is not kind of some abstract philosophy that I'm talking about. This is impossible to avoid in fundamental physics, in fundamental research, because it's in most of the experiments you perform, if your material is sufficiently clean and you give it the right environment, you will see some form of emergence. And, you know, this kind of jumps to different fields, this concept of emergence. It's spoken about in biology, in chemistry, in a various number of fields. So it's not some abstract kind of topic which you should poo-poo. And, you know, to bring this to the realm of materials, when I'm talking about emergence, you know, we've documented through time a number of physical paradigms which both continue to surprise us and, for example, are very difficult to model mathematically, have a lot of experimental quirks, or just exceedingly difficult given our current computational prowess, our ability to do you know, calculations at this time. So the frontier, if you will, of modern society, you know, we're not talking about the Wild West of yesteryear where we were trying to cross the continent. We're talking about the idea of discovering new phases of matter, and these are hidden in these condensed matter systems. And the idea is to, you know, the paradigm is to couple different degrees of freedom. And when I say degrees of freedom, I'm talking about like these elementary physical concepts that we have. And we know spin of an electron, charge of an electron, orbital, excuse me, I'm sorry about that. The orbital character of atoms, the lattice, this is what the crystal looks like. All of these things, we try to pull them together and we try to bring out something which is exciting. Here's just a graphic that's taken from some piece of literature from my colleagues. And here's two examples. Quantum computing. This is a fascinating regime of research, which has been very much in the realm of fundamentals, but is very quickly transitioning to applied. Google, IBM, Microsoft, all of these companies, Amazon, these companies are heavily investing in the engineering aspect of taking, the demonstration of quantum coherence and really scaling it up and trying to build up a real computer that works and can solve problems that classical computers can't. And another example is superconductivity. Everyone's seen this, right? You've gone to a science fair and you see like a levitating magnet. Well, this is related to superconductivity. This is the perfect screening of a magnetic field, and it expels this magnetic field and it'll sit there levitating as long as it remains superconducting. But this is an inherently emergent property. This was observed experimentally to begin with, and it took a long time to explain theoretically. It comes about as a character of a lot of carriers interacting with each other and talking to each other through some form of interacting term in their energetic. So let's talk just for a moment about superconductivity. I call this the wild world of superconductivity because it really is wild. Like what happens in these superconducting materials continues to just stimulate so much research. A very good portion of the solid state physics community spends entire careers dedicated to looking for the details of superconductivity, how superconductivity competes and all these type of things. So I'm going to give you a short rundown of kind of the history of superconductivity. So of course, superconductivity came out of just a mad experimentalist's enthusiasm for pushing the limits, to boil it down. This was Chameleonis. He got the Nobel Prize in the early 20th century. He was in the Netherlands trying to cool down material as low as he possibly could go, pushing the limits. I pushed the limits in terms of purity. This scientist, he wanted to push the limits in terms of temperature. He wanted to go as cold as possible. What I'm plotting here is this is the critical temperature of superconductivity. So this is basically when a material goes from being a metal to turning into a superconductor. And you can tell this in experiment quite easily. I'll tell you how this happens in a moment. But you'll notice this is a very low temperature, right? This is Kelvin. This is like 4 Kelvin or something like this. So 0 degrees Celsius, 32 degrees Fahrenheit, is 273 degrees Kelvin. So this is about minus 270 degrees Celsius. So it's pretty chilly. This is around the temperature where liquid helium, where helium becomes a liquid, where it goes from a gas to a liquid. And, phases of matter do this all the time. You go from gas to liquid, solid. So he was trying to, liquefy helium, push the limit, go as low temperature as possible. And he was measuring mercury. He was measuring the resistance of this mercury while doing this experiment. And all of a sudden, there's a sudden change in the resistance of this material. And the hallmark of superconductivity is that the resistance disappears, right? So you can measure a superconductor and you can measure the voltage drop from one end of the superconductor to the other, and you see that there's no voltage drop across the device. And if there's no voltage drop, that means no energy is being lost in the material. The voltage is building up because you have a difference in the chemical potential on both sides. The voltage is, it's higher on one end, lower on the other, and this is because the electrons are losing energy as they go through the material and scatter. This is what I was talking about before, this limitation of scattering. But superconductors at low temperature, they just have this emergent property where these electrons pair up and they talk to each other and they don't scatter anymore. And he saw this anomaly where the resistance of mercury fell to 0. He thought it was, something wrong with the experiment. Reproduced it. Other labs reproduced it, and they found out it was real. This is a real property of materials at very low temperature, superconductivity. Now, a lot more materials, and he got the Nobel Prize for that. A lot more materials have since been discovered to be superconductors. Here's, lead, niobium, niobium nitride. There's a whole bunch of them down here. You see through time, right? It's kind of slowly going up. There's some wacky materials down here. This is like uranium, beryllium, uranium, platinum, really kind of abstract areas of the periodic table now. But then in the 80s, there was a big moment in condensed matter science, or in science in general, where suddenly these very complicated materials, lanthanum, barium, copper oxide. This is not some simple material like lead. This is a complex material which has this complex crystal structure here. It's got, this has yttrium in it, but it's a very similar material. You've got these layers of copper, oxygen, barium. This is kind of a dirty old ceramic, at least in the beginning. This was found to be evidently superconducting, and the authors were very hesitant to claim this. It was published in not a particularly famous journal, and it was published using very hesitant language, because there was no reason to suggest that such a complex material, such a dirty material, would be superconducting. And especially because copper, even though copper is a very nicely conducting material, copper itself is not superconducting. This is one of the wacky things about it, right? But again, this was reproduced, and suddenly we're dealing with temperatures at kind of, 150 Kelvin or something. So this ushered in the era of what's called high temperature superconductivity. So that's kind of, tickling your brain thinking, oh, maybe we can get to room temperature. We'll talk about that in a moment. But fundamental physicists came in there like, okay, maximizing TC, that's all well and good, but let's study the parameter space a little bit bigger. So what I got here on the right-hand side, I'm not going to go through this in great detail. This is temperature versus hole doping. This is basically the number of electrons. Again, you keep hearing these numbers of numbers of electrons and size of the crystal and these type of things, all materials related parameters. The blue area is the superconducting area, and you see all these different shaded colors. This is antiferromagnetism. This is pseudogap. This is what we call a strange metal. This is what we call a Fermi liquid. These are all distinct emergent electronic phases that come out from interacting particles that you can't just explain from looking at a single electron. Each of these regimes, the amount of PhD theses that have been dedicated to studying these regimes is an immense number. And this continues to this day. This is from a few years ago. This continues to be one of the hottest topics in physics. So, now we've discovered high TC, high temperature superconductivity. This is now, taking us to a new direction. We're not quite there yet, but the transistor took a long time. So don't count us out yet. But, one of the dreams that we have in condensed matter science, there's a few holy grails, I call them. One of them is quantum computation, and we're going to get there very, very soon. One of them is room temperature superconductivity. Room temperature superconductivity would completely revolutionize our lifestyles, because suddenly you could have an electricity grid that has, superconducting wires taking an immense amount of current from the Sahara Desert all the way to Europe. It can go to Asia, wherever. We can bring it over to the US, and you wouldn't lose any energy in the process. And then you can think about putting superconducting coils inside these electric motors, for example. And anything to reduce the amount of dissipation in these materials has dramatic impacts when it comes to the overall energy efficiency of our society. So, we're still at low temperature at the moment. We're heading towards room temperature very slowly, and I'm not going to place a bet on when it's going to happen. It will happen, and hopefully it happens in a way that is amenable towards industrial scaling and dissemination in society. So I'm going to wrap up in just a moment. I'd like to just add a few personal notes about why I think fundamental research is very important. And I'm very much channeling my supervisor of my previous job. When I was working in Germany, I had the great privilege of working with a Nobel laureate, and he discovered what was called the quantum Hall effect. And his name is Klaus von Klitzing. I strongly encourage you to listen to his YouTube lectures. He's a very inspirational character when it comes to motivating you towards fundamental research. And it's difficult sometimes to justify the large amount of time and resources which are required for fundamental research, when they may appear perhaps more pressing, if you will, applied issues that should be solved. one answer I would have with regards to, one rebuttal I would have with regards to that perspective is that fundamental research is very much like, grandma's recipe for some, delicious meal that she has, right? She'll tell you it's like a pinch of salt, a little bit of this, a little bit of that. She knows exactly what's going on, but she can't put it in writing. Fundamental research in many ways is very similar. Scientists go to great lengths to document details, keep lab notes, publish as many details as possible. But at the end of the day, a lot of the details of these very intricate, very exploratory, very risky experiments are handed down through some form of kind of quasi-oral traditions, handed down through labs. And this is why it's important to collaborate, to travel, to talk to as many scientists, young and old, as possible to convey these ideas. And, here's some things, like a lot of people go through various experiments. It doesn't work, but you don't know that until you talk to someone about it, right? There's tweaks that you're doing in the experiment. And one of the very poignant comments is something like, this could display interesting characteristics in future experiments. And this really was proven to be a very important and very astute observation in a recent scientific breakthrough in 2018, which was discovered when graphene, which is a special type of semiconducting material or half metal material, was found to be superconducting in a special device geometry. But a few years before that, there was one line in a theory paper saying that, if you do this, it might be interesting. It didn't go into great details, but it kind of preempted this huge breakthrough, which completely revolutionized how we look at that class of materials. So, having these discussions amongst peers is a very important thing, and continuing this tradition and investing in this is a very important thing. And the final thing, just to leave you with a quote, is related to, more abstract applications. And the quote is related again to Bell Labs, beautiful device discovery and inventions coming out of Bell Labs. A laser is a solution seeking a problem. Now, that kind of, you're like, well, we see lasers everywhere now, right? And that's the whole point. When Myman discovered this, he quoted, or invented this, I should say, he made this quote because it's like, well, okay, we have these little chips or whatever, and they can, these devices which can blast out a huge amount of light with a very high Q factor, a single wavelength. And it's, we have all these, from an optical point of view, it's a beautiful device. But what are we actually going to do with this, right? We've got electrical cables running here and there. Optics is not particularly useful. What I'm showing you here is now this is the fiber optic network, which underpins all of our, information technology in society. This is 2023. This is all the undersea optical networks which we've laid around the world. And none of this would be possible without the laser. This is shooting photons of light, carrying all of our digital information around the world. So fundamental research, it comes about a year later, a decade later, a century later, who knows? But these building blocks that we lay now ultimately do contribute to revolutionary breakthroughs at some point in the future. So this is all that I wanted to say. I'm very happy to take any questions that you have, general or more specific. And thank you very much for listening. I appreciate your attention.
Thank you, Professor Falson, for that informative talk. If you don't mind, stop sharing your screen really quickly.
Sure, yeah.
Just so we can, for the sake of the recording. Okay, perfect. Yeah, we hope this talk was educational for all of you, whether you're already interested in this research field or if you're just exploring STEM. And so next up, we actually have a couple of questions for Professor Falson that are guided Q&A, which has actually been curated by our speaker series team. So as you all may know, one of the main goals of STEM Chats is to promote educational equity for young people in STEM. And something that we found really unique about Professor Falson's journey in STEM is that he's been a student and a researcher across so many different countries. And so we were wondering if you could talk a little bit about your college and post-college education, and how did that sort of impact your future, and where were you educated as a student and a researcher?
Sure. I'm very happy to. So if you'll just let me share my screen for one moment again, and then we can return to yours. So yeah, as Abby noted, I've to borrow another physics word, I've been delocalized for a long time. And this is kind of, I don't want to use the word proud, but I don't regret any of my choices, and I think I've come out better because of these choices. So I did grow up in Australia. I hope that you've understood my accent. I grew up in a small country town, and I went to a good school, not one of these, hyper competitive private schools in the city. I worked hard to get into a good university. I went to university in Sydney. I did my undergraduate degree there in chemistry. And then I eventually moved to Japan after this. And I'll give you some reasons in a moment. I'll just brush over kind of my story of how I got here. I went to Japan. I spent a year in Tohoku University and did a short master's degree there. And then I used to move to the University of Tokyo and did a PhD in materials science. And after graduating, I moved to Max Planck. This is a government laboratory in spread. There's many Max Plancks in Germany. They're outstanding facilities for doing fundamental research where you're limited only by your imagination. This is where I did what's called a postdoc. So this is kind of a relatively short-term research tenure. I was there for about 4 years. And then after, working there, I moved to Caltech at the start of this year. So there's a little bit of backstory here. So actually, when I was a high school student, I was very enthusiastic to do medicine. I was attracted to medicine. And ultimately, I went to university and was a med student, taking clinical classes in the hospital, taking chemistry classes, physics, math, kind of, the first year of medicine is kind of basically a science degree. And then was not particularly enthused about what the future had to hold for me. And at that point, I decided that I was much more attracted to the hard sciences, the hard natural sciences, and more specifically, hard condensed matter physics. And when I say hard, I don't mean difficult. I mean hard as in a dense sense, not a soft sense. And this is why I'm talking about crystals and these type of things. So I completed my bachelor's in chemistry, and I was very much working in the realm of taking courses in the direction of solid state devices, physical chemistry, materials, thermodynamics, these type of things. If you recall this library, the books that I had at the beginning, I was kind of very much in the middle there. But I really wanted to study abroad for my PhD, and I wasn't particularly fussy about where that was. I just wanted to go abroad. Maybe this is kind of an outcome of, being born on an island in a small country town. You kind of just want to spread your wings and travel as much as possible. Australians are pretty well-traveled people. So I applied to various scholarships, and I very luckily received a very generous scholarship from the Japanese government. I think that they were happy to see an applicant. Not that I was the only one, but I gauged from their from the interactions that they were very happy to see an applicant who was very much interested in STEM. This was a scholarship program set up by the Japanese government after the war, and this was kind of very much aimed at kind of mending international ties. So they invite international students in. You can study in Japan. A lot of people go there to study Japanese culture, and this is a great way to promote cultural exchange. But I really wanted to go there and learn materials physics. And the Japanese are famous for being excellent crystal growers. So I went there and joined the group, moved universities halfway through, stayed in the same group, and I had an absolutely fantastic time growing materials, growing crystals. So, as research, research evolves, and it's very important that everyone understands this, right? And especially when you begin your grad school endeavor. As you're coming out of high school, you very much think that science is an exactly solvable issue. Then you start to do undergrad courses and you're like, oh, hold up, solving this is really difficult. And then you start to go, towards grad school, and you're like, wow, I can only, like, solving this is going to be, it's going to take the rest of my life to solve this. So you just kind of nibble away at it. And this is why the community is important. A PhD overall kind of similarly evolved. So I was doing a lot of crystal growth. And then ultimately I had the opportunity to go to Max Planck in Germany in a collaborative stance and measure there a lot, most of the electrical characteristics of very low temperature. And they have outstanding facilities at Max Planck. And this led to a very positive relationship developing. And I would travel there regularly as a student. And this naturally led to the opportunity to seek employment there after graduation. So I joined MPI as a postdoc and spent 4 years there, as I said. So again, I'm working on different topics, same field, different topics as a postdoc. And you start to think about, what do I want to do next? And, I did this half by design, half by luck. I began to garner a fairly broad range of skills. I think that put me in fairly good stead to take the next leap in my career. And I was, generally speaking, attracted to North America because I feel it gives young scientists a fair amount of freedom and, to borrow an Australian term, fair go. It gives, they vest a lot of trust in junior scientists. And I think that's a very healthy thing for scientific society, because junior scientists are very ambitious. We work hard, we work long, we take risks. And a lot of the breakthroughs, a lot of the hard work is done under those constraints. So I was very lucky to obtain this position at Caltech, and I'm hoping to, bring, an amalgamation of all of these skills that I've gathered over these various locations and develop this into a new lab. So, my education has been fairly scattered in a sense. I don't think that's necessarily a bad thing, because I always followed my heart. I always followed what was interesting. I always followed and pursued what I was willing to spend a lot of time on, because this is what I think people, junior people coming into STEM or who are interested in STEM, you need to understand that this is hard work. This is not hard in, back-breaking labor of laying bricks or digging holes. This is hard work intellectually, and it's frustrating work because you can spend years on a problem. When I moved universities from Tohoku to Tokyo University, it took me 1 or 2 years to reproduce my results. This is grinding work that you have to be very dedicated. Now, I'm not trying to pat myself on the back here. What I'm trying to say is that I loved the work. I loved the day-to-day. And I never had an issue of getting out of bed in the morning and being like, oh, I don't want to go to work. So that feeling, avoiding that feeling of I don't want to go to work, has been kind of my guiding principle to getting me to where I am at this point in my career. And I really strongly suggest that people follow that in thinking about where they want to go in their career. Compensation, salary has not been a major motivator for me. It may be for some people, especially from different backgrounds. I came from a nice middle-class family. I was very lucky that I didn't have to, we were not wealthy, but I went to a state university, I went to public school, and I got a scholarship. So my education has not been a large financial burden on my family. But I understand it's not always the case. But fundamental research, you have to be willing to put in the long hours and be dedicated to these difficult problems. This is one very strong word of advice that I could lend. I'm not sure if you wanted to ask follow-ups there, Abby, if you'd like further clarification or something.
No, I think that was really important to talk about how the international journey might be different than, students like us who are staying possibly in the United States.
Sure. So yeah, exactly. Look, I chose to come to the US because I think it is the best place for young scientists. But that doesn't mean I'm under some illusion that, the the only place to do science is the US, because it's clearly not the case. Science should be inherently a collaborative thing. And, you know, there are sub-disciplines, there are sub-communities, like hyper minuscule divisions within each field of hyper specialization in each field of science. And these small groups of very highly skilled individuals tend to clump together, and they tend to clump together in different locations. So I know that we have some audience members from Cornell University here today. You know, I'll state that Cornell has been one of the most outstanding universities historically for low temperature physics. It currently is one of the most outstanding universities for materials physics, for thin film deposition. You'll be able to find some outstanding members of the faculty in the material science division. So, you know, each university has its strengths all around the world. So, you know, as an undergrad, you don't get many opportunities to travel and to go to conferences and these type of things, but you should definitely take every opportunity that you get. You know, conferences, you may ask, what's the point of a conference? You know, conference, usually you get to go somewhere very interesting, kind of a touristy location. You give a 1-hour talk and you spend a week or something there. And it's a fantastic time because you get to give your talk, you get very stimulating questions, you have usually a very intense, sometimes confrontational discussion about it. But then you get to have dinner with your colleagues, you get to go on hikes with your colleagues, you get to spend time with them, and you get to know them as people. And this is what leads to collaborations. This is what leads to, you know, the seeding of new ideas. So generally speaking, interconnectedness is extremely important. And, you know, I think that my somewhat unconventional path to get to where I am has kind of given me perhaps a little bit of a leg up in that front, if you will. But, you know, if you're born, raised in the US, you're going to get a great education. But, you know, please do try to travel. Please do try to collaborate. That's what I can suggest.
Yeah, absolutely. I actually wanted to open up questions for the audience because I know a couple of them have questions to ask. So for those of you who are listening in the audience, if you would like to ask a question, we encourage you to use the raise hands function in the participants tab, and we'll do our best to call on you sort of in the order, and you'll be able to unmute yourself and show your video if you'd like to ask a question like that. Otherwise, you can also directly message me if you'd like to ask a question anonymously. And reminder that the session is still being recorded. So if you do unmute and turn on your video, just a reminder that this is being recorded by STEM Chats. So yeah, I will open it up to the audience. Feel free to raise your hand or send me a message through the chat. I think Annie has a question.
Oh, okay. Good evening. I'm here from New York City. Hello, Professor.
Hi, Annie. Thank you very much for asking the question.
I have a couple of questions. Hi. No problem. So I have a couple of questions. First off, why was it considered as a quote unquote dirty science? I've missed that part.
Sure. I mean, this just, you know, I'm sounding like a broken record here. I apologize. The material was dirty. You know, back in those days, people that were working on semiconductors were kind of frowned upon for dealing with, you know, very uncontrollable samples, and each sample was different, and you didn't get reproducibility. You know, the core of the scientific method is, you know, reproducibility, right? You do an experiment once, you do it again, you do it a third time. If all three line up, you've got pretty good reason to believe it's going to happen a fourth time, and then you're okay to report the results. So these materials that they had back in the 40s, the crystals were just not pure. So that's what I mean by a dirty science. It was just kind of, it was an immature field of research, and it needed disciplines to come together. You know, the chemists had to show up and say, oh, we can pull those impurities out. The theoretical physicists had to show up and say, yeah, now we can explain these the electrical characteristics. And then the device people had to say, yeah, now we can make the contacts and make the device. So all of these things had to come together. But there was a bit of a leap of faith, if you will, to kind of say, no, I'm going to work on semiconductors, because it was not, it was very embryonic.
I see. Okay.
Does that answer your question?
Yes, it did. Next one was, what was the backstory to the years listed on the graphs, the ones with multiple small bell-shaped curves?
Let me try to share my screen, if you will. And okay. I think I know what you're talking about. And if it's true, then you're going to regret asking that question. This one.
What?
Annie, is this the question you're asking? Is this the data you're asking about?
Yes. Yes.
Okay. I mean, I'm only joking that you're going to regret asking that question, because this is the pride and joy of my scientific career, and I can talk for hours upon hours about every detail of this. There are a number of advancements. A lot of these were technical advancements, making the equipment better. And then a lot of them were chemical advancements, in that you had to perform the growth procedure better, if you will. So, for example, from 2007 to 2009, this big improvement in electron mobility, this was related to changing the apparatus, basically. We went to a much more controllable procedure. And as a result, you reduce the amount of defects or impurities. These are kind of fairly synonymous things. The amount of cracks, or the amount of random atoms or whatever is inside the crystal, by approximately 1 order of magnitude. From going from 2009 to 2010, this was basically a chemical advance. This was a lot of time dedicated to comparing how much of material A you want to put in, how much of material B you want to put in, what's the temperature, what's all of these kind of experimental details. So this is the scientific method here. This is making. I've only got 6 data points here, and for the green curve, but probably there's maybe, I don't know, 500 or something that are not shown. There's a ton of samples to actually get from here to here. Now, from 2010 to 2010, this was published in the same year, but actually the data was gathered at a slightly different time period. Usually publishing takes a little bit of time. So this was, again, a chemical advance. This was going to a much, much purer precursor material. The precursor material was ozone. Now, everyone's heard of the ozone layer. Ozone is a molecule called, it's a metastable molecule, O3. So instead of O2, which is the stable molecule of oxygen, you have an extra oxygen, which will sit attached and will detach relatively easily. So what you can do is you can actually pull up this ozone and use it as a chemistry for your, as a precursor material for your chemistry. And it's nice because ozone, it's just ready to break apart. You give it a little bit of heat or any reason, and it'll have a reaction very happily. Whereas oxygen, you have to, it's a relatively stable molecule. So we were able to, reveal that by growing using ozone as opposed to oxygen radicals, which was what we were previously using, we could again reduce the amount of defects dramatically and go from the green to the yellow. Now, from the yellow to the red, this was grinding chemistry of just, purifying every single detail of how the sample is held in place, how the sample is heated up, how much of the material you want to spray on the surface. There was a number of subtle improvements that were made from here to here. And then 2019, even though this is not the peak value in terms of electron mobility, you'll see that this is the lowest number in terms of electrons. And this is actually a very difficult thing to do, to make a material that has both low number of electrons and high electron mobility. So this is just basically a representation that this is the limit that we can push in the low electron direction. And it actually happens that for reasons, I'd have to discuss in another talk, when you have a low number of electrons, that's when the emergence is the strongest. This is when you have the strongest emergent physics and when the most unexpected character is revealed.
Got it. I have two more questions.
I think we're slightly, I want to actually bring, oh, sorry. I think we have to have, I've gotten a couple more questions from anonymous people who want to ask questions anonymously.
Annie, what I can recommend is if you want to send me an email, I'll be happy to answer any of your questions.
Thank you so much.
Yeah, we will open up for those of you who have additional questions. We'll also be accepting additional questions after the session, and we'll have a way to get back to all of you with answers as well if you guys would like. So yeah, one anonymous question from a student is, what have you learned from your students in your time teaching at Caltech? Thanks.
So I haven't taught, so when you become a professor, you know, the viewpoint of duty of a professor is a little bit different from what a more junior student may perceive, let's say. Teaching in the classroom is one very important thing. This is a core responsibility of being a professor. And then teaching more in a one-on-one sense in a laboratory environment is something very different. So in a classroom, what I've learned is that teaching is very difficult when you try to teach fundamental topics. Now, I remember being an undergrad and just kind of, you know, digesting information extremely quickly. And now kind of the tables are turned and I'm having to go back and restudy this and try to re-educate you know, the junior students about these topics. And it mostly goes okay, but sometimes you are posed very simple questions which are very difficult to answer. And this has taught me that actually, generally speaking, they are the most important questions to ask, because very complex questions or very higher level questions often brush over the details, are not understood by everyone. And, you know, you can kind of have those in a more one-on-one discussion. Whereas more general questions, you know, if you're amongst an audience or something like this, or addressing the fundamentals, leads to a much more kind of, you know, holistic understanding of scientific topics, if you will. And, you know, I've learned from my students by being asked very difficult, basic questions that when I'm an examiner now, I try to reverse, you know, I try to flip it around and ask really basic questions on them. And what I've learned is that they don't always understand the basics, right? The basics are often the most difficult to explain. So what I want to do, and you know, I'll be the first to admit, I've got a lot of teaching development ahead of me. What I want to do is develop my ability to teach these basic topics well. Now, in the lab, I think that it's pretty similar, actually. You know, my lab is just getting up and running. You know, all of this data that I've shown you, this is from my previous studies. We're really just beginning our journey in my new lab at Caltech. I want to teach my team the basics. I want to teach them a thorough foundation. Because, you know, a thorough foundation is what leads to a well-rounded scientist that can jump between different fields. And this is what is really important. You know, this is going back to the library again. You don't need one textbook in your brain. You need like 5 to 10, right? So if I can educate my people on the basics across chemistry, physics, you know, a few different realms, then I think they'll grow and mature into very independent thinkers. And that's what I want. You know, I don't want to have an environment where I'm coming in the morning and I'm like, you know, okay, you're going to do this first, and then after lunch you're going to do this, and then later on you're going to do that. That's not what I want. I want to be able to discuss with them and say, what do you think? How are you going to solve that problem? Tell me what, you know, what's next? I want them to be independent, because then, you know, ultimately I want them to be better scientists than I am. That's the whole point of educating these people and having them go off, get faculty jobs or go to companies or something and really contribute to you know, the scientific community in their own way.
I believe Justin has a question.
Hi, I'm Justin. Hi, Professor Falson.
Hi, Justin.
Hi. So I'm curious about why you chose to pursue your research at Caltech specifically, rather than other universities like Cornell, which you mentioned was also active in quantum materials research. Thank you.
Yeah, I mean, that's a great question. What I often tell my people in my group, in my class, generally speaking, is that, to speak in a scientific sense, in any decision or any action or any competitive situation, there are a lot of parameters at play. You are not in control of like 99% of those parameters. And therefore, there is no point in being stressed or, trying to control these parameters because it's just physically impossible. Now, one example I'll give is, when you are a university student, or we can go back to high school. It's at every level, right? You are going to write an application to universities. You're going to write an essay. You're going to get your best SAT scores. You're going to try to put together an application that you think is the most solid, application that you can muster up, right? You'll get into some universities. You won't get into some, and kind of, the universe needs to decide. The royal universe, parameters outside of your control. The same is going to happen when you apply to grad school. You're going to work really hard. Hopefully you get a publication, you get some research experience. You're thinking, I kind of like chemistry. I kind of like physics. Like, you don't really know. Don't put too much pressure on yourself as well, right? It takes a long time to figure out what you're really passionate about. Maybe I should have mentioned this before. It took me a long time to figure this out. And then, you're going to apply to all these grad schools and you might not get into 2/3 of them, even if you think you're going to get in, right? And this is just because in a faculty meeting, they're looking at various parameters. It's not just your GRE, it's not just your GPA, it's various things that you don't have control over. Maybe they're not taking students that year. Maybe they don't have a strong professor in the field that you're interested in, right? Exact same thing happens when you're looking for jobs, right? I applied to Cornell. I didn't get the job there, right? I applied to Caltech. I got a job offer there. I applied to various universities. So ultimately what you need to do, if you're going to be a successful scientist or a successful, person in STEM, not even scientist, you have to understand statistics and you have to play the statistics. You have to keep moving forward, do the best you can, and just believe that statistics is going to work in your favor at some point in time. So, that's the honest answer. It's not like I turned down an offer at Cornell. I love Cornell. I'm a great friend of Cornell.
Thank you.
Looks like we have a question from Nikita.
Hi, Professor. I was wondering, why is it important to have a vacuum in the molecular beam epitaxy?
Very good question. Two answers, basically speaking. One of them is, I've been talking a lot about purity, right? So if we want to take this effusion cell material and put it on this substrate, right? And we want it to be pure. We want everything on this substrate to be pure, right? Do you think you can do that if this chamber, if you're breathing on the substrate and you're putting your fingerprints and stuff on this? You can't. You have to treat this like surgical grade clean, right? So by pumping all of the air out and all the water out and all of these things, you're just making a clean environment, right? You're trying to reduce the amount of impurities that eventually go into your crystal that are sitting here. Now, the second answer is just generally much more physical in that, I want to spray my material from here to here directly. Now, if you take a spray can outside and you put a canvas 10 meters away and you spray, those particles are not getting to that canvas, right? It's just going to hit the air and you're going to get a cloud of paint and you're going to be covered in paint in no time whatsoever. So you pump this air out just so basically you can push this effusion cell material onto the substrate and it doesn't run into anything else. this is what's called the mean free path of these gaseous species. It's just basically how far they can go without running into something else. So you just want the purest environment, the cleanest environment, I should say, and then the ability to go directly from the effusion cell onto the substrate without having some like intermediate chemistry or something like that.
Oh, okay. Thank you.
All right, I think in the interest of time, I know it is 6:30 or 9:30 EDT for those of you on the East Coast. But I think we have one more question actually from the YouTube live stream that I would like to pull up. So somebody has asked, did you ever consider going into industry instead? And could you still probe basic research in industry with potentially less hard work it takes to establish yourself?
The answer to the first half is yes. I did consider going into industry. You know, like as I said just a moment ago, it took me a long time to figure out what I was interested in. And I think that I only kind of became dedicated to my direction when around kind of here, when I started seeing data come from these green splodges down here to up here at yellow, I started to go, oh, hold on, my samples are starting to get pretty good. This might lead to something very interesting. Now, you know, that was partially hard work, but, you know, I was lucky. The universe very much worked in my direction. There's some experiments that just don't work. And this is one of the great challenges of being an experimentalist, knowing when to cut an experiment and just be like, I'm done. Time is the most valuable thing that we have. It's not money or anything like that. It's time. So, you know, having that ability is something which everyone needs to work on throughout their entire career, and especially if you're a professor or a supervisor or something like that. So maybe I can add that to kind of what I want to be able to teach to my students. So, you know, I started to get these results and I thought, okay, this maybe has legs. I might continue this. But up until that point in time, I was very much open to going and working in industry, because I think, you know, there is a lot of amazing results that come out of industry. Like, you know, I'm kind of selling you on, you know, fundamental research is amazing and we do all these crazy, crazy things, right? But I mean, this is absolutely breathtaking. I cannot overstate my respect that I have for these scientists that have achieved such a perfection, you know, a perfect understanding of this material system and being able to make these incredibly complex devices, which really improve the quality of life for everyone, right? You can feel this in everything you do every day. So I was very open to going to industry. Now, my mentor was pushing me more in the direction of fundamental research and at a university as well. So, you know, one thing, if you go into undergrad, definitely try to pair up with a mentor, a professor, and try to, you know, interact with them as much as possible. Do some research if you can. And then when you're in grad school, you'll be doing research intensely, but really try to absorb as much knowledge, not just pure like textbook knowledge, but, you know, wisdom. Try to absorb as much wisdom as you can from your supervisor, because they've seen a lot, right? They can guide you in many ways which are very difficult to kind of pinpoint with words or numbers or something like this. Now, in terms of fundamental research in industry, you know, I want to tread lightly here because it's I don't know the full story. I will say that, you know, Bell Labs was the basic research wing of AT&T. It was around before the war. It was very instrumental in the war, in the Second World War, and it continued after the war. And, you know, like the transistor came after the war, the laser and these type of things. But, you know, before that, they were working on vacuum diodes, vacuum triodes, the undersea cable, all of these things, all of these fantastic things that you can read about in this book. There's similar basic research labs which existed all around the world. Philips in the Netherlands, NTT in Japan, and these places still exist to a certain degree, but my naive perspective, and I'm equally probable, it's equally probable that I'm just uneducated on this, is that these labs are shrinking rather than growing. Now, what you can do, kind of an intermediate step between, you know, a university environment where you have teaching responsibilities and these type of things, and an industrial setting, is something like a national lab. Or, for example, something that we have at Caltech is called the Jet Propulsion Laboratory, and this is a wing of this is a research lab which is funded by NASA but is managed by Caltech. And this is where, you know, a lot of amazing fundamental, like kind of, you know, the real borderline between fundamental research and applied research is done, in the sense that they work on these very fundamental missions to, you know, different planets and these type of things, right? So that's kind of the applied sense. It's not an industrial applied sense, but it actually has a specific purpose. But they're plumbing at very fundamental and new approaches of doing these, of solving these type of problems or making these types of devices. So national labs are somewhere in between the university and the industrial setting. So, I mean, the short answer to your question is that yes, you still can do fundamental research at a non-university environment. Yes, you can. Now, whether or not it's less effort, I don't know if that's the best way to look at it, or if even I could make a statement on that, because I think the amount of effort that you put in is really kind of up to you at the end of the day as an individual. You can work for as long or as short as you want. Maybe you have a more structured work schedule if you work at a national lab or industrial setting. You know, at universities, usually it's quite unpredictable how your day-to-day is going to be. Aside from the teaching duty, it's fairly dynamic and unpredictable. So that may not be for everyone.
Awesome. Thank you so much, Professor Falson. I would like to share my screen now.
Sure.
Sorry. Awesome. Okay. Oops. Okay. For some reason. Okay. Awesome. And again, thank you so much for Professor Falson for being here and giving us an amazing talk. It was really interesting and very educational, very valuable. And now I would like to introduce you into our speaker series teammates, Abigail, Bianca, Kirsty, Zainab, and Lola, me. And once again, thank you, and please follow us on Instagram and LinkedIn, and subscribe to us on YouTube, where you'll be able to rewatch this event, the live stream of it. And please fill out this post-event survey that we have also dropped down on the chat, and where you could also leave your additional questions to Professor Falson. We'll get back to you with an email of the answers. Thank you so much, everybody. Thank you for attending this event.
Thank you, everyone. And thanks organizers again.
Awesome. Glad to have everyone here. I'll leave the screen just in case if anybody wants to take a picture of the links or QR codes.